I'm going to talk a little bit about the science background for Cal. There's a number of grand themes that run and play out in science over many decades. For example, for several centuries, astronomers have been building ever bigger telescopes to look further and further back in time and deeper out into the universe. Physicists for much of the past century have been building larger and larger particle accelerators to reach higher and higher intensities and to look again deeper and deeper into the heart of matter. I'm going to talk to you about another of the great themes of physics, the quest for ever colder temperatures. And especially I'm going to talk about the Cold Atom Lab, which represents the latest step in that journey towards absolute zero. One of the early pioneers in this field is the 19th century Scottish scientist, Sir James Dewar. He invented the famous Dewar flask, and he developed technologies to reach lower and lower temperatures, culminating in the ability to liquefy hydrogen at temperatures of about 20 degrees above Kelvin, 20 degrees above absolute zero. As an aside, scientists like to talk, physicists in particular, like to talk in Kelvin. That's how we like to measure temperature. It's referenced to absolute zero, so zero in Kelvin is absolute zero compared to zero in Celsius, which is the melting point, the freezing point of water. The magnitude of each degree, a degree Kelvin and a degree Celsius, is the same. Anyhow, after Sir James Dewar's breakthroughs, following that, there was breakthroughs by Heinrich Onnes of Netherlands, who was the first person to liquefy helium, and soon after he discovered superconductivity, the ability in certain metals for currents to flow in the total absence of resistance. A few years later, during the infancy of the science of quantum mechanics, Bose-Einstein developed the theory of the Bose-Einstein condensate, which we're going to spend much of the lecture talking about. And this is, theory told how certain types of particles would behave at temperatures very, very close to absolute zero. When it first came out, this theory, not too many people believed it really corresponded to anything physical. Even Einstein didn't really believe it. But as people started discovering the laws of superfluidity and superconductivity, they realized that it related to these investigations by Bose and Einstein. In the 1980s, techniques were made to cool atoms with lasers and reach temperatures of a millionth of a degree above absolute zero. And that rose a lot of excitement in the field that possibly we could finally observe this predicted state of matter. But it took another 10 years before Eric Cornell and Carl Wyman at the University of Colorado developed a new set of techniques that allowed them to finally observe this condensate. At the time, I was a postdoc. Had just started a little earlier than that in the lab of Bill Phillips. And as soon as this result came out, everybody in our lab, or at least a large fraction of us, sort of stopped what we were doing, and we started trying to make condensate machines. And this not just our lab, but many labs around the world kind of joined into this rush. And that excitement has not let up. After 20 years, this has provided an extremely diverse area of physics. And we'll learn a little bit about some of that diversity as I go on in the talk. So James Dewar, of course, there's no way he could have predicted all these exciting things that would have come from this journey towards absolute zero. And as we kind of take the next step, kind of go a little bit closer and a little bit cooler temperatures, we have to expect that possibly nature will have some surprises for us as well. Now, I should state, Sir James Dewar's contributions are very important, of course. But in truth, if the truth be told, he's actually not even the greatest inventor named James Dewar. That honor goes to the American inventor, James Alexander Dewar. who developed the Twinkie. So what is a Bose-Einstein condensate? To understand what a Bose-Einstein condensate is, we have to recall a few facts from the science of quantum mechanics. That's the science of very small objects, atoms and molecules and subatomic particles. And quantum mechanics teaches us that all matter has both a wave and a particle nature. That's associated with any quantum object. There's a wave function, and that the wavelength associated with that wave function is inversely proportional to the momentum of that particle, and hence inversely proportional to how fast it's moving. And that wave describes the probability of finding that particle in a particular location or a particular state. At high temperatures, atoms behave pretty much as particles. If you have a gas of molecules at room temperature, they're shooting around like bullets being fired out of a high-velocity rifle. And that classical behavior, you can just think of them as billiard balls. Their wavelengths are so short that we don't have to worry about quantum mechanics, and we can just think of them completely classically. As we reach colder temperatures, we reach the types of temperatures that we can reach with laser cooling, we start to see that quantum nature. The wavelengths get bigger and bigger, and it becomes more pronounced. And there's a transition that occurs at temperatures of a few tens of nanokelvin, where the wavelengths of neighboring atoms starts to overlap. Now, remember that wavelength of that atom tells the probability of finding the atom in a particular location. As soon as those wavelengths overlap, you can't tell which atom is which anymore. And you have to look into, you have to treat all these atoms are identical. And that was the insight that Bose and Einstein had come up with. So when you reach that point, the atoms undergo a phase transition. So a phase transition is, you're all familiar with the transition from liquid water to ice. That's a type of phase transition, one state of matter to another state of matter. In a Bose-Einstein condensation, that's a phase transition, a purely quantum phase transition, in which you transition into a state where a large fraction of the atoms are in the lowest possible energy level available to the state. And all of those atoms, their waves are perfectly in phase and coordinated with one another. That process of making BECs is now done routinely in hundreds, if not thousands, of labs around the world. And many people are reaching these types of temperatures. Going into microgravity, as we'll see, allows us to reach a new regime of temperatures that ultimately might get as low as a picokelvin. That's a trillionth of a degree above absolute zero. At temperatures like that, the wavelength becomes on the order of about a millimeter. And that's just an astonishing thing, that a quantum wavelength could be that big. The one thing that people tend to know about quantum mechanics is that is the science of very small things, tiny things like atoms. But at these temperatures, these objects can actually be extended. This is the observation of our first Bose-Einstein condensate in a prototype of the CAL apparatus in our ground test bed up the hill. This is a series of pictures that we take. We shine a light on the atoms, and we look at the shadow cast by the atoms, and we can measure a density profile of the atoms. And this is 3 different measurements as we lower the temperature, bit by bit. And you see as you go through this transition, as you pass this critical temperature, you very suddenly see this spike shoot up of nearly stationary atoms in the center of the cloud. So how do we get there? What are the techniques that we use to achieve these cold temperatures? We actually have a whole sequence. So there's a series of different techniques that we use. And we start with a technique called laser cooling. This, might surprise most people. We think of lasers as things that we can cut with or that we can weld with, even do nuclear fusion with lasers, right? So how can lasers make things colder? To understand how that works, we need to understand 3 basic facts. The first is that we can push on things with light. Light carries momentum, so you can imagine things like solar sails to zip around the universe, zip around the galaxy. We can imagine, and this is the same types of forces that produce the beautiful tails on comets. So light can push on objects. It carries momentum, and it can push on things. And then the next fact is that atoms are very particular in terms of the colors of light that they absorb. This is the spectra of rubidium. The very first spectra was actually taken by Robert Bunsen of Bunsen burner fame. He's the person that first discovered rubidium, I believe. Rubidium, if you try to shine light on rubidium, it'll only absorb at these very sharp lines. If you actually change the wavelength of the light that's impinging on a rubidium atom by a part in a million, it'll go from strongly absorbing to just barely absorbing at all, almost totally not interacting. So that's the second fact that we need to recall, is that the colors of light absorbed by an atom is very sharp lines. It's only very sharp lines. And then the third thing that we need to remember is that color absorbed depends on the motion of the atom because of the Doppler effect. We're all sort of probably familiar with the fact that if you listen to an ambulance siren as it's moving towards you compared to when it's moving away from you, it sounds different. The reason it sounds different is that when it's moving towards you, those wavelengths are compressed. They're a little bit shorter. When it's moves away from you, those wavelengths are stretched and they're a little bit longer. Likewise, with light that's absorbed by an atom, if the atom is moving towards the source, it'll strongly absorb light of a slightly shorter wavelength, what's called blue-shifted light. And if it's moving away from a source, that light will be redshifted. It'll be the wavelength absorbed by the atoms will be longer. So we can put all those together and just understand laser cooling. When we want to cool atoms with lasers, we have a pair of lasers pointing on our gas of atoms. And we tune both of those lasers so that they're a little bit to the red, a little bit longer wavelength than those atoms really want to absorb. So they're a little bit more red colored than the color the atoms really want to absorb at. So if an atom's just sitting at rest, it barely feels the force from either of those atoms. But if the atom happens to be moving towards one of these lasers, because of the Doppler shift, it will see that light shifted towards the light that it wants to absorb at. So it'll more strongly absorb from this laser beam. That'll provide a force on the atom, which will slow it down. We can extend this into 3 dimensions very easily, with 6 beams kind of coming from all different directions. And this proves just amazingly effective, more than one could kind of possibly hope for. And the most amazing thing about this probably is the fact that we can achieve these temperatures as cold as a few millionths of a degree above absolute zero in an amazingly routine manner. In thousands of labs around the world, scientists can walk into that lab and literally it's almost a flick of a switch, and you have a sample of atoms, at a few millionths of a degree above absolute zero. Now, I said at the beginning that most people, when they think about shining lasers at things, this is not just laymen, but scientists, when you tell them that, if they're not in this field, would imagine that things would get hotter, right? And it's true. It actually is true. There is a heating mechanism. And to actually figure out the temperature, where we get this millionth of a degree above absolute zero, we have to balance a heating effect from the lasers with this very powerful cooling effect. And that leads to temperatures in this range. If we want to go better, if we want to get colder, we have to turn the lasers off. And so the way we do that is we use a technique called evaporative cooling. We put the atoms into a magnetic trap. We can prepare the atoms in a state where they act like a little bar magnet. So they have a north side and a south side, and they can be pushed around with magnetic fields. And if you can set up your magnetic field so that there's a minimum in that field, the atoms will be trapped there and they'll be attracted to that minimum. In Cal, we produce those fields with something called an atom chip. It's a piece of silicon, and it's got wires printed on it, just little metal wires, and we run currents through those wires, and that produces a magnetic field that we can use to trap the atoms. Inside that magnetic trap, now the atoms, it's like they were inside a cup, and the cold atoms are kind of bouncing around the bottom. The hot atoms kind of make it up, higher and higher up the walls. The cold ones are down here, the hot ones kind of bounce up like this. And we can selectively pull off just those hottest atoms by shining radio frequency or microwave frequencies at just the right, if we tune it to just the right frequency, we can just pull off just these hot atoms. The rest of the atoms will cool down and equilibrate at much lower temperatures. It's something like blowing on a cup of coffee. When you blow on a cup of coffee, you're helping the hottest atoms to escape from the liquid, and that brings down the whole temperature of the coffee. So how do we measure temperature? There's several actual methods that we can use to measure temperature, and we can compare them to make sure that we're getting everything right. But the simplest way to measure temperature is simply to turn off our magnetic fields and release those atoms. So the atoms are sitting there in a cup, and we finished cooling them, and they're pretty cold, and we want to see how cold they are. We can just very quickly turn off that magnetic field. When we do so, those atoms, that cloud of atoms starts to expand, and the hottest atoms move the furthest and the fastest, and the cold ones are left behind. We can just wait a little while, and then we take a quick snapshot of what's going on with the atoms. And just by measuring the size of this cloud, we can tell the difference between a hot cloud and a cold cloud. Again, these images are taken by looking at shining light on the atoms and looking at the shadow cast by those atoms on a camera. This evaporative cooling technique is used in many labs around the world. We want to be the coldest spot in the universe or close to it. And so we use some other techniques that kind of fall into the realm of what I call advanced cooling to get even colder temperatures. And the first one I'm going to talk about is something that goes by the rather exotic name of delta kick cooling. It acts really more like a freeze ray, so I like to call it a freeze ray. But what we do is we just let go of our atoms, and they expand just like we were going to measure the temperature, right? And the hottest atoms, after a little while, have moved the furthest, and the cold atoms are left behind. We can then snap on another magnetic potential for just an instant, and we can, if we turn that magnetic field to just the right strength and in the right position, we can we can provide each of these atoms a little bit of a kick, such that the atoms that are far away here, far over here, and the hottest ones receive the biggest kick, and the atoms that are left behind receive a much smaller kick. And so they're all kind of instantly sort of frozen into space. Another technique that we can use is a technique called adiabatic cooling, where we just let that cup, that magnetic trap, we just get it weaker and weaker and weaker. And if we do that slowly enough, as that gas expands, it cools down. This is similar to when you spray on an aerosol can, and the aerosol can gets colder as you do that. This, again, can be done on the ground, and we do it fairly routinely to try to lower our temperatures that we see. But you're limited in how well you can do it on the ground. On the ground, you always have to support against gravity. You have to hold the thing up against gravity. So that limits how weak you can make those traps, and it limits how well you can use this technique. We have a number of PIs on this project. These are external folks that are doing science investigations. The first one I'm going to mention is Cass Sackett, because he is actually helping us trying to research the ultimate limits of this adiabatic cooling technique. So we combine all these techniques into all these different stages of cooling, different types of techniques into the cold atom lab, and you've seen pictures of it that Anita showed. It's a mini lab in space. The idea is that we give researchers a large suite of tools, many of the same tools that they use in their own labs on Earth, and we try to put those into this facility. We have, for example, the ability to trap 2 different species of atoms, rubidium and potassium, and 2 of the different potassium isotopes as well. We have the ability to look at the atoms from 2 different directions and to, with high and low resolution. We can prepare a variety of states, and we have ability to actually tune their interactions, and we'll talk more about that in a bit. But the basic idea is to kind of give scientists just a versatile set of tools that they can carry out just a wide range of very different experiments. As we talk about some of the experiments that our PIs are going to do, you'll kind of get a sense of the breadth, both of the field and what we're able to do with the cold atom lab. Why do we do this in microgravity? So the kind of dream of atomic physics is, for centuries, it's been this way, that we want to create a sample of atoms, and we want to just have them sit there motionless while we look at them for as long as we want to, right? So we want them completely unconfined. We don't want any magnetic fields or lightweight fields on them, so that those would also disturb them a little bit. We don't want them to bouncing into walls and things like that. We just want them to just sit there, just to stay put. And we want to look at them for very long periods of time. If you try to do this on Earth, so you can get pretty cold temperatures on Earth, but if you try to just kind of let the atoms go, they'll go plop to the bottom of your vacuum chamber, and you'll get a fraction of a second typically is your time to look at them. And as people make tricks to get a little bit longer time, but you're sort of fundamentally limited in how much time you can look at them. In Cal, in microgravity, these atoms should just hang around for, we hope to something like 5 seconds. But one of the ideas behind Cal is that, it could be improved. We'll have follow-on missions, and these things can be improved upon. Ultimately, the limits could be hundreds of seconds. So I started, thinking about Cal, back in, as soon as I came to JPL. It was a couple of years after being a postdoc, and I've been working on, almost my whole career. Even right from the beginning, even before the space station had been put together, just a couple of years after BEC had been discovered, I was trying to pitch this idea that we could have this BEC lab up there. And so this project, me and my colleagues have been developing, a lot of that technology. Our effort, got off strong for a few years, and then because of issues with the space station program, we kind of stopped doing this type of research for a while. The Europeans, in particular, German groups, have continued this and have had a very steady, long, and very successful program, actually preparing Bose condensates and studying them in microgravity. First in drop tower experiments, where they have these 200-meter towers and they drop the whole apparatus to get a few seconds of microgravity, and also in sound and rocket experiments, where they can get hundreds of seconds of microgravity. The goal in Cal, though, is to just be up there and have hours and upon hours that you can tweak things and fiddle with things and get them just right, and have much longer duration of microgravity. One of the technologies, and it's sort of the killer app for ultra-cold atoms in space, is a technique called atom interferometry. Some of our most sensitive measurements are made with light interferometers. Probably the most famous is the LIGO detector. That's light laser interferometry gravitational observatory. And there's 2 of these, one in Washington and one in Louisiana. And last year they observed the first signal of a gravitational wave formed by 2 combining black holes. These types of interferometers use physical beam splitters and mirrors to interfere beams of light to make these exquisitely sensitive measurements. An atom interferometer is a little, does kind of the opposite. We actually use beams of light to split up atomic waves, and then other beams to reflect them and recombine them. So we have, atoms coming into this apparatus. We shine on a laser beam. When we shine that laser beam, we can arrange its strength so that the atom has a 50% chance of going this way and a 50% chance of going that way. Quantum mechanics says, if you haven't made a measurement, you have to assume it's in both at the same time. So the atom is actually physically in two different places at exactly the same time. That's a little mind-boggling if you think of atoms as particles. It's not so strange if you think of an atom as a wave, though, right? If you get at the beach and you see a wave kind of coming into the beach, it's spread out, right? And if you have a wall that juts out into the ocean, half of the wave can go on one side, half of the wave can go on the other side. That's not, such a big deal. The thing to wrap your head around is, how can something be a wave and a particle at the same time? How can these things actually be in two places at once? But we then recombine these waves, and when they recombine, they interfere. So this is a very ubiquitous process with any type of wave phenomenon. That when you combine two waves, they will either cancel each other out or they will enhance each other by what's called constructive or destructive interference. So they produce fringes, and by monitoring these fringes, we can make these very sensitive measurements. Already on the ground, we get measurements of things like accelerations and rotations and gravity that are as good as you can make with almost any other means of making them. But the fantastic thing is, how much better these things get when we go into space. When we go into space, we get to look at the atoms for much longer. So on Earth, the way we do these experiments, typically if we toss the atoms in the air, and they have about a half a second or so that we can make an interferometer. We have one of those here at JPL. In space, though, we can get, in CAL, we'll get a couple of seconds, but in future missions, we might even get hundreds of seconds. For some types of measurements, for example, for gravity or an acceleration measurement, the sensitivity of that measurement goes as the square of the amount of time that you have to look at it. So you can have this huge possibility of making incredible types of measurements. These types of instruments will yield this, basically a new generation of exquisitely sensitive quantum sensors. They can be used for things like testing fundamental physics, some of the fundamental ideas of Einstein and some of the ideas behind things like dark energy. But they can also be used for real-world applications. We can use them to monitor Earth's gravity. So JPL has a mission now called the GRACE mission that monitors Earth's gravity using a pair of satellites that orbit around the Earth. And that can measure things. They can weigh the ice sheets. We have a follow-on mission that's going to go on called GRACE follow-on. But in the future, we might use these types of sensors with a little bit more development. These might be very competitive or significantly improved over what we can measure. That allows you to make very important measurements relating to climate, but we might also fly these around some planet and look for resources that future astronauts might want to use, or we might search for oceans under Europa and all kinds of interesting possibilities. And that brings up to the basic idea of various applications of absolute zero. One of my favorites has always been the atom laser. An atom laser is a source of coherent matter waves, just like a laser is a source of coherent light waves. And these were discovered and been observed on the ground. This is one that we observed something like 10 years ago. And another scientist was the first had observed them significantly longer before that. But these, they don't do that much on the ground, because it's very strongly perturbed by gravity. In space, we might imagine, a whole world of applications for them in atom optics and things like matter wave holography. Probably one of the killer applications for them would be as a source for for an atom interferometer, though. I now want to kind of turn to some of the Cal science, some of the science investigations by our principal investigators. So we put this facility together with all these kind of standard tools, and then we invited scientists to come up with proposals of how to do it. And we were very impressed with the quality of the proposals, the quality of the science team. Really, Cal has probably one of the most prestigious science teams that NASA's put together for any mission. This is a study of few body physics in microgravity. It's led by Eric Cornell. He's one of the people on the team that first made the first Bose condensate. Peter Engels works with him, does a lot of the heavy lifting on this particular project. Debbie Jin started with this project, and we were very honored to have her. She's a very prominent scientist, really the leading expert in the world on cooling potassium, and she was the first person to make a fermionic condensate, and she was a MacArthur Fellow. Tragically, she died last year, and we're all sort of very sad about that. This experiment searches for sort of universal features in the way a few bodies, 3, 4, 5, come together and collide, and it looks for bound states between those molecules. And because it's universal, you get the same behavior with gases of potassium as you would with a gas of, say, strontium or something like that. Or even, in some cases, you can see universal behavior between how atoms behave and things like neutrons and quarks behave. What's very profound about these types of experiments are they can give us some insight into how complexity arises in the universe. So if we listen to our particle physicist friends, they are convinced that the universe is very simple. There's just a few fundamental particles, and they obey just a few simple rules. And they also tell us that the only thing that ever happens in the universe is these fundamental particles bounce off of each other as they collide. So how can you get from that simple physics that we believe, we don't know for sure because we don't yet have that final theory of physics, but one of the driving principles of theoretical physics is that physics is simple, and we always look for these simple solutions. But so what could lead to all the complexity that we see around us? Galaxies and forests and trees and symphonies and things like that. How can that kind of complexity arise from very simple underlying physics? And we can kind of get an insight into that by looking at this realm of few body physics with 3, 4, 5 atoms, and then try to work our way up to understanding more complex systems. Another team, and this team features 2 other Nobel laureates, Wolfgang Ketterle, who, independent of Eric Cornell and Carl Weinman, developed one of the very first Bose condensate apparatuses and did a number of landmark studies with them. And Bill Phillips, who was one of the pioneers of laser cooling, are both working with Nick Bigelow, who is heading a fairly large consortium, lots of different, very prominent scientists. And in particular, Holger Mueller is kind of doing the most of the thinking about this one particular experiment. So he has a number of ideas of how to test Einstein using atom interferometers and in space. And one of the ideas is to just look at, kind of repeat Galileo's famous, we don't know if he actually did it or not, experiment where he drops 2 balls off of made out of different material off of the Leaning Tower of Pisa and shows that they fall at the same rate. And the idea is, can we drop potassium atom and a rubidium atom? We're going to drop them, up on the space station, and they'll fall for a couple of seconds. And during that time, in orbit, they'll go about 8 miles around the Earth. And at the end of that, we can measure them to within sort of a fraction of the wavelength of light, about 100 nanometers or so with an atom interferometer. The importance of this is Einstein's theory is predicated on gravity acting on all particles exactly the same. And so if we can see a difference, that might point the way towards some theories beyond Einstein. Jason Williams of JPL has a really nice a study planned of what we call halo molecules. So one of the really interesting things about ultra-cold atoms is that we have techniques to very precisely control how strongly they interact. So if you just look at a gas, atoms in an ordinary gas, they may repel each other, they may be attracted to each other by a little bit or stronger. But with these types of systems, we can actually control that. We can make them attract very strongly, we can make them attract very weakly, we can make them repel or very strongly or very weakly. By making the interactions very, very low, we can actually observe what we call halo molecules, and these are the most weakly bound of any kind of diatomic molecules. They can be on the order of a micron, which is an astonishingly large size compared to typical molecules that we see. And Jason has a number of ideas of things that you can study with this very interesting system. We have another team that is trying to study, led by Nathan Lundblad of Bates College, which is trying to study bubble quantum states. These are spherical quantum states, so hollow bubbles, a condensate kind of spreading around that type of trap. We know how to produce a potential that would make a bubble. But if we try to do that on Earth, this is what we find. This is actual data that we took in our test bed, trying to use parameters that represented what Nathan was interested in doing. And what you see, instead of having this, you have this circular potential, but all the atoms sit down at the bottom, and it's so not terribly interesting. In microgravity, they would spread out over an ellipsoid. And it's a very complex system, lots of possibilities of studying interactions and excitations and maybe putting in multiple atoms and watching them how they interfere and things like that. It'll be a very rich set of physics from this state, which can only be observed in microgravity. But as Anita pointed out, we've designed CAL to be repairable by the astronauts, and it's also upgradable. So we can bring in new technologies, new types of lasers. We can bring in a whole new vacuum system with new geometries for our magnetic traps and new ways to aim lasers into that trap. Or put other types of systems in it. So it really leads to sort of a limitless potential for possible future investigations. And with that, I will turn it back over to Anita.